This is a tutorial for week 4. We've been talking about algorithms, and one type of algorithm that we talked about is a function that calls itself, which is called recursion, if you recall from the lecture and the notes. And if you just kind of want to follow along, you can go to the home page and the tutorials for week 4, and we're going to go through the recursion slides. Now, recursion is interesting. Not only is it a useful tool, but it's beautiful. It's interesting. You know, we might say that it's elegant. And so it's worth thinking about in the practice of making computers do work for you, to have a thought about efficiency, of course, but also elegant solutions to create that efficiency. So the kind of philosophy here goes that, you know, if you learn a little bit, you learn enough to get yourself into trouble, you know, you can solve a problem. You can make the computer do some work, but it takes a little bit of reflection to resolve some problem elegantly, and that's what we strive for. And that sounds like something that that's a hurdle I have to get over, and there's the pressure of people evaluating my code. But actually, here's the good news. The good news is that thinking about trying to achieve elegance in these solutions is really fun. It's really fun. It's the most fun part of writing code. So recursion is one of these elegant solutions that that is both interesting and also easy to write the code. You can write simple code, and it's also easy to visualize how it works. So recursion is very common, and for almost every recursion problem, maybe every recursion problem, let's take a tick back from what I'm about to say. For every problem in computer code, there are basically infinity ways to implement it. Different languages, different algorithms, efficient ones, sledgehammer ones, and elegant ones, you know, and the details of the code, there are infinite solutions. Well, recursion is not unlike that. It fits right in where, you know, we don't have to use recursion. It's considered a very elegant way of solving problems where it's possible, and but it is possible to solve many, maybe all, recursion problems with some kind of loop, you know, a strong-arm sledgehammer approach. Now, the definition of recursive functions is very simple, which is part of the elegance of it, and it's just a function that calls itself. So we did talk about one of them in lecture and in the notes. The notes go into a little more detail than the lectures did, but one of them is the factorial function, this mathematical operation that's you know, some integer exclamation point that that multiplies itself by itself, decremented by one integer. So, you know, factorial 5 is 5 times 4 times 3 times 2 times 1. Of course, we drop the times 1 because it's just itself times 1. And that's 120. But you know, that's trivial to do in your head, but you could scale this up and it becomes a non-trivial problem that you need a computer program for. So the factorial function we use to notate mathematically as n exclamation point is defined over all positive integers, right? And it's the positive integers less than or equal to 1 all multiplied together, decremented by 1. And we're gonna, even though we looked at it just here briefly, we're gonna define a function called fact that takes an input of a positive integer, and we're gonna look at how it works. Well, you know, we need a program that that performs a calculation like this. That if we're going to calculate the factorial of 5, we need factorial of 1. We need factorial of 2, 2 times 1, factorial of 3, 3 times 2 times 1, and so forth to get to factorial 5, right? So what we could do is we could say that factorial of 2 is actually 2 times factorial 1. And likewise, 3 is factorial 3 is 3 times factorial 2. Likewise for 4, likewise for 5. Well, there's a pattern here that you can see that we can exploit to create an elegant recursive solution. And this is one where we have factorial n will equal n times factorial n minus 1. We can look at that on the previous slide again, where factorial of some number n, 3 in this case, is 3 times factorial 3 minus 1, factorial 2. Well, this is the basis for a recursive definition of the factorial function. Every recursive function has at least 2 cases that apply that cover the basis for any input. And the base case, which is triggered, then terminates the loop, terminates the process of calling itself. The recursive case is where the recursion, actually occurs. So for factorial, we need to define the base case, and we need to define the recursive case. What's the base case? Well, if n is equivalent to 1, we just return 1, because factorial of 1 is 1. Now we need to define the recursive case, the elegant part of this, and we already did look at that, and we're going to return n times factorial n minus 1. Okay, so this is the classic factorial algorithm. Now, in general, we use these to replace loops to create these elegant solutions. But we could use a loop. And here's an example of a different version of our factorial where we define some integer of 1, initialize it, and while n is greater than 0, we store our calculation in our product variable that times, we use the shorthand for that variable times itself for the new value of n, and then we decrement the value of n each time. This will accomplish exactly the same thing. Try it. I encourage you to try these in your own console. You should do that for all of these algorithms to get used to them and help you remember them. Well, it's also possible to have more than one more cases rather than just the base case and the recursive case. You can have multiple ones. We're going to look at an example of that. For example, the Fibonacci sequence, where we might define some first element as 0, some second element as 1, and then we have the nth element up to an arbitrary number as the sum of n minus 1 and n minus 2. Okay, and this is the case where there are multiple base cases, but we're going to look more closely at a solution with multiple recursive cases. Okay, so the Collat's conjecture is one. If you haven't heard of this, it's a very simple kind of idea, and it applies to positive integers, and it speculates that you can get back to 1 if you follow some steps. So whatever the arbitrary n is, we test it, and if n is 1, we stop. Otherwise, if n is an even integer, we divide it by 2, and we go back to the loop. Okay. Otherwise, if n is odd, we multiply n by 3 plus and add 1. So n times 3 plus 1, and then we go back to the iterative process. And remember, what we're trying to do is get back to 1 in this. So, you could stop the video here. You could write a function that does this and has a particular outcome. And so we can look at like a table of what it is. If our input is 1, we check to see, our first step is to check to see if n is 1. And in this case, it is. And so we would stop there. Now, if n is 2, we it's not 1, so we go to the next one. It's an even integer, so we do that one. And what do we do with even integers? We divide them by 2. So here we'd start with 2 divided by 2, and we'd get 1. For an odd integer, it's weirder. We multiply it by 3 and add 1. Okay, so this is an iteration for the condition input 3. And what we do here is we take 3. It's not 1, and it's not even, so it's odd. So we're going to multiply it by 3 plus and add 1. It gives us 10. Click back up to the function. 10 is not 1. It is even. We divide it by 2. We end up with 5. 5 is odd. We multiply it by 3 and add 1. That's 16. 16 is not 1. It's even. We divide it by 2. That's 8. 8 is not 1. It's even. We divide it by 2. It's 4. 4 is not 1. It's even. We divide it by 2. It's 2. And so forth. We end up with 1. Now, what is going on here? What's the Collatz number? Well, it's the number of steps required to get back to 1. And so for 1, requires 0 steps. For 2, it requires 1 step. For 3, it requires 7 steps. That's kind of like the idea. So hopefully you took the challenge up to write your own function. But one solution is like this. We define our function that takes an input of an integer, call it Collatz, and we have different conditions. Here we're going to implement this with a if-else-else, and if n equals 1, we return 0. Good. For even numbers, else if n, and remember this is the remainder operator. So if we divide n by 2 and that equals 0, it's an even number. And in that case, we're going to return 1 plus the result of Collatz n divided by 2. So this is the recursive part. And if it's odd, we return 1 plus Collatz 3 times n plus 1. Okay, so this is an example of several examples of recursive functions. This idea is very important. They're fun to achieve, if you allow yourself to do it. Play with this. And that's all I have to say about that.